This is first lecture on moment of inertia. We are going to deal with areas. There is also something like mass moment of inertia, wherein you do the similar things but with the mass. But here our interests are specifically in areas. And this lecture covers the basics of it. That is the definition and little bit of prerequisite which is required to solve the problems. Now let's try to define it. Let's try to define moment of inertia. Moment of inertia is defined by these two integrals. Ixx, that is moment of inertia about x axis, is given by the integral y square dA. And moment of inertia about y axis is given by integral x square dA. Now please note the definition. Look at the area and look at that small portion dA. Now when I am dealing with Ixx, I multiplied this dA with y square, meaning area I am multiplying by the distance square. So if I want moment of inertia of that small area dA, it is simply y square dA. And if I want the moment of inertia of the entire area, I integrate it, so I get of the entire area. Similar definition, look at Iyy. It is x square dA. X is the distance of the dA from y-axis, and therefore it is x square dA. So moment of inertia is area into the distance square. And again, if you integrate it over the entire area, you get the moment of inertia of this total area about y-axis. This is a basic definition. So what it amounts to, it's just an integration. It's just an integration. Why we study it? Because this integration keeps appearing in many further courses. So it is almost like one of the properties of area. And therefore we evaluate this integral for standard areas, as well as we develop capacity of evaluating this quantity, moment of inertia, for various combination of the areas. Now before taking this course, some kind of prerequisite is there, and that prerequisite is for standard areas. See, here is a rectangle of width b and height d. We should know from our previous knowledge the value of these integrals for the centroidal axis of these areas. Now let's read. X-axis, horizontal axis, passing through the centroid of the rectangle, Ixx has a value 1 by 12 BD cube, whereas for y-axis it is 1 by 12 dB cube. Just the cube is interchanged. Now this can easily be evaluated, but our interest at the moment is we accept these results and we assume that this integration and the basic derivation has been done before. Doesn't matter if you don't remember those details. All you have to know is the result at the moment, and that is about x-axis and about y-axis, what is the value of moment of inertia for a simple rectangle of width b and height d. Now what we know for rectangle, we should also know it for other standard figures. This is a triangle. It's similar. We have centroidal x and y axis, and what was 1 by 12 is now 1 by 36. That's the only difference. So Ixx is 1 by 36 BD cube and Iyy is 1 by 36 dB cube. Come to circle family, starting with full circle. You see there centroidal x and y axis, the values of moment of inertia about these two axes are same, and they are pi by 4 into r raised to 4. For quarter circle, these numbers are 0.11 by 2 r raised to 4 for both the moment of inertias. And for the semicircle, the values for Ixx and Iyy are different. For Ixx, it is 0.11 r raised to 4, whereas for Iyy, it is 1 by 8 pi r raised to 4. Now you see, what is expected is we remember these values. It's not a tall order, because see, rectangle and triangle just differ by 1 by 12 and 1 by 36, and for circle family you have to remember pi r raised to 4 by 4, pi r raised to 4 by 8 and 0.11. So a little bit effort, little bit time in looking at the slide, you will be able to retain these formulas with you. Now in addition to these formulas, what we need is what is known as Parallax Theorem. We must understand what it is because we need its application all the time in this chapter. So let me explain. Let there be x-axis axis, which is the central axis of the area shown. Let me take a small elemental area dA at a height y from the x-axis axis. Now if I have another axis which is parallel to x-axis axis at a distance d, then moment of inertia of this area about this new axis mm is given by y plus d whole square dA. Reason? The basic definition. And what was it? The area into distance square. Now if you look at the figure and see how much dA is away from axis mm, you will find that that distance is y plus d. So we square that distance, multiply by dA, integrate it over the whole area, and you have moment of inertia of this entire area about the new axis, the mm axis, which is at a distance d from the centroidal x-axis axis. Let's expand this. Let's expand this square so that this bracket so that we get some compact expression. When we expand, we have y square dA plus 2yd dA plus d square dA. Let's look at each of these terms little closely. The first term, y square dA, if you see from the previous slide, it is nothing but Ixx. The last term, d being constant, taken out of integration, it is d square integral dA, which is nothing but d square into a. And the middle term, which is integral 2yd into dA, is 0. Reason? If, and of course only if, xx is the centroidal axis, then you will agree that for every dA at a distance y, there is another dA at distance minus y. Then only xx can be centroidal axis. And if I add up all this, because integration is after all summation, you are bound to get this net sum as 0. And therefore we come up with a very powerful formula, that it says that moment of inertia about axis mm, which is at a distance d and parallel to the centroidal x-axis axis of that area, then that moment of inertia is equal to Ixx plus ad square. That is moment of inertia of centroidal axis plus the area into the distance square. Distance between two axes, you are squaring and multiplying with the total area. Now you are now well equipped with these two, that is the standard formulas and Parallax Theorem, to solve any problem on planar moment of inertia. Now that part will continue in lecture 2 and lecture 3 on this topic. Now you see, there are only two types of problems. In the first type, you are given some axis and you are asked to find moment of inertia about that. In second type, you are asked to find moment of inertia of the centroidal axis of a new figure, which is combination of standard figures. We will look at these two in the second and third lecture. Thank you.